Welcome to the Deep Dive. We're here to unpack the big issues and sometimes the surprising solutions shaping our world. Today, we're focusing on something absolutely critical: water scarcity.
Hmm.
It's genuinely staggering. You've got over 2.2 billion people right now without safe drinking water access.
It really is. And the projections are even more worrying.
Yeah, they're talking 5 billion people by 2050. That's huge. And it hits hardest in those underdeveloped, landlocked, or sort of off-grid places, you know?
Exactly, where the standard water infrastructure, the pipes and plants,
Yeah.
just isn't there or can't keep up.
So we need different ideas.
We definitely do. And that's where this idea of atmospheric water harvesting, AWH, comes in. It's got a lot of people excited.
Right, pulling water straight out of the air.
Basically, yeah. Condensing the moisture that's all around us into drinkable water. Sounds a bit sci-fi, maybe, but the science is solid.
Okay, but it hasn't been smooth sailing, has it? I mean, earlier attempts, they faced some real problems.
Oh, absolutely. Big roadblocks. You had like really low water output, sometimes just tiny amounts, a few milliliters a day.
It's hardly practical.
Not at all. And then there were safety worries, like releasing lithium ions, which is obviously a major concern. Plus, they just didn't work well when it wasn't very humid.
So, great idea in theory, but tricky to actually make work reliably and safely.
Precisely. And that's what makes what we're diving into today so interesting.
Okay.
We're looking at a really new device developed by researchers like Chang Lu and Xuan Zhao, published in Nature Water. It seemed to tackle these exact problems head on.
So, our mission today is to really dig into the engineering, the material science behind this thing that could potentially change water access for millions.
That's the plan. Exploring how they might have cracked it.
All right, let's do it. To really get why this new device is such a big deal, we probably need to understand those earlier challenges better. What were the main things holding back AWH before?
Well, you basically had two main kinds of materials people were trying. First, these things called metal organic frameworks, or MOFs.
MOS.
Think of them like microscopic sponges, super porous structures. And they're great. In some ways, they grab water vapor really quickly, this sorption process.
Right.
And they can even work when the air's really dry, like down to 14% relative humidity.
Wow, that's very dry.
It is. But the catch, they're rigid. They don't swell up. Water just kind of sticks to the surface inside the pores.
Ah, so there's a limit to how much they can hold.
Exactly. Their capacity is limited by that stiffness, and they don't adapt well if humidity changes. Those tiny pores, good for dry air, actually restrict the total volume.
So good for super dry conditions, but limited capacity and flexibility.
I see. What was the other approach? Hydrogels.
Yes, hygroscopic hydrogels. Now, these do absorb water into their whole structure, and they swell up nicely, which means they can often take up and release water faster.
Okay, that sounds more promising capacity-wise.
Yeah.
But you mentioned safety concerns. Big ones. Two major issues really held back the older hydrogel design.
Uh-oh. What were they?
Hmm.
Especially if we're talking drinking water.
First issue was leakage. A lot of these gels used salts like lithium chloride, LiCl, because it's really good at attracting moisture.
Makes sense.
But the salt could actually crystallize and leak out of the gel, especially if you stood the panel up vertically.
Not good. Salty water, presumably.
Yeah, potentially. And worse, the crystallization itself stopped the gel from swelling properly, so it became less efficient. A double whammy, really.
Right. Stops working and contaminates the water. Okay, what was the second, maybe even bigger issue?
This was the real deal breaker. Lithium-ion contamination.
Ah, the lithium ions again.
Yeah. In those earlier designs, lithium ions, the Li plus Ni, could actually get carried along with the water as it evaporated from the gel.
So they ended up in the collected water.
They did,
Yeah.
at concentrations between 20 and 100 parts per million.
Okay, is that bad? How bad?
It's really bad. The safety threshold set by the USGS and EPA here in the U.S. is just 0.06 parts per million.
0.06 compared to 20 or 100.
Exactly. Way, way over the safe limit. So the water they produced just wasn't safe to drink.
That's a non-starter. Okay, so previous hydrogels, some water, but potentially leaky, possibly inefficient, and definitely unsafe.
Pretty much sums it up.
Which brings us to this new atmospheric water harvesting window, the AWHW. This is supposed to fix all that.
That's the claim, yes.
Mhm.
It's designed to be totally passive, no external power needed beyond sunlight, practical, scalable, and it looks kind of like a window.
Interesting.
And its breakthrough comes down to basically three levels of innovation working together.
Okay, let's peel back the layers. Tier 1, the material. What makes this hydrogel super stable and safe?
So the core is this unique mix: polyvinyl alcohol, lithium chloride, and glycerol. PVA legal glycerol. It's a ternary material, three parts working together.
Glycerol, like the stuff in lotions.
Kinda, yeah. But here it plays a crucial role. It acts as a phase stabilizer. Remember how the LCL salt wanted to crystallize and leak out before?
Yeah, that was a big problem.
Well, the glycerol basically stops that from happening. It keeps the LBL stable within the gel matrix. It prevents those crystals from forming.
Ah, clever chemistry.
Very. And this stability is key. They tested it for 340 cycles of absorbing and releasing water. That's about a year's worth of daily use, and found no floating liquid, no crystal issues.
Okay, so that tackles the leakage and stability. What about the lithium contamination? The safety issue?
This is maybe the most important part. This PVA legal glycerol hydrogel is designed to be non-porous.
Non-porous, how does that help?
Think about it. If there are no pores for the water vapor to travel through on its way out, the lithium ions, which are dissolved in the gel's water, physically can't escape into that vapor phase. They're trapped in the bulk material.
Oh, I see. They can't hitch a ride with the evaporating water.
Exactly. And the tests confirm it. The water collected from this AWHW consistently had lithium levels below that crucial 0.06 ppm safety limit.
So it's actually safe to drink this time.
That's the finding, yes. A massive step.
Okay, huge leap on the material front. Now, what about the structure? You said it's not just flat. Something about origami.
Yeah, this is really neat. First off, it's vertical.
Vertical, why?
So water can absorb and evaporate from both sides of the panel at the same time. Potentially doubles the speed compared to a flat horizontal setup.
Smart. Okay, but the origami part, does it actually fold itself?
It does. It's a self-generating origami array. As the hydrogel absorbs water, it swells, and this swelling action naturally causes it to buckle into this repeating dome-shaped pattern, like origami.
Wow. Okay, why? Just to look cool.
Well, it does look cool, but it's incredibly functional. This folding increases the surface area massively, about 3.1 times more area compared to if it were just flat.
More surface area means more contact with the air.
Exactly. Faster water absorption, faster release.
Brilliant. And you mentioned something about smart heat management, too. How does folding help with heat?
Right. It's not just about area. The shape helps manage heat efficiently. When it starts evaporating, the peaks, the apexes of the domes, get warmer first. But as it dries a bit, the valleys become warmer. This creates localized heat transfer within the structure, helping drive evaporation efficiently and minimizing how much heat is just lost to the surrounding air.
So it directs the solar heat where it's needed most as the process happens?
Kind of, yeah.
Oh.
It optimizes the whole solar evaporation process.
Okay, that's seriously clever design.
Absolutely.
So stable, safe material, self-folding structure. What's the third tier? The enclosure, the window part.
Right. The whole thing is housed in this window-like chamber. It creates a controlled space inside, optimized for the water to evaporate from the gel and then recondense so you can collect it.
Makes sense. Keep it contained.
And it's tilted at 90 degrees vertical, which helps the condensed water droplets run down easily for collection.
Okay. I also saw something about a special film on the glass. Radiative cooling. Sound a bit contradictory if you need sun.
It does sound it, but it's another clever bit. It's a coating, PVDF-HFP. Just two things at once. One, it lets the sunlight through, so the gel heats up for evaporation photothermal effect. Two, at the same time, it's really good at radiating heat outwards, specifically in certain infrared wavelengths, out towards the coldest space.
Like a one-way heat valve, letting sun in, letting waste heat out.
Sort of. It allows the condensation surface, the inside of the glass, to get slightly cooler, maybe 0.5 to 1 degree Celsius cooler than it would be otherwise. And even that small difference helps more water vapor condense back into liquid.
Wow. So it helps evaporation and condensation simultaneously?
Precisely. Fine-tuning the thermodynamics.
And there's an aluminum base, too.
Yep. That acts as a heat sink. Helps pull heat away from the condensation surface, further encouraging water collection, especially when the sun is shining directly on it.
Okay, this whole system sounds incredibly well thought out. Material, structure, enclosure, all working together.
It really seems to be a holistic design.
But the ultimate proof is in the pudding, right? How does it actually perform out in the real world, especially in tough spots?
That's the crucial question. So they took it to Death Valley.
Death Valley. Can't get much tougher than that for dryness.
Exactly. Early November 2023. The average humidity was only 21%, sometimes dipping down to 18%. Super arid.
Get to work.
It did. It produced 57 milliliters of water per day.
57 mils a day in Death Valley conditions from just air.
Yeah, and this is significant because it's apparently the first time a practical hygroscopic hydrogel system has been shown to produce water in such low humidity.
That's a milestone. What about high humidity? Does it handle that too?
They simulated that as well, around 88% relative humidity, and there it produced 161.5 milliliters a day.
Whoa, much more.
Yeah, which they say surpasses other passive AWH devices reported so far, so it seems to work across a range.
Okay, extreme dry, extreme wet.
Hmm.
What about just like a normal city?
They tested that too. Cambridge, Massachusetts, July 2023. More moderate conditions, it produced 56.5 milliliters per day there.
Similar to Death Valley's number. Interesting.
It is, but when you calculate it based on the area of the device, it works out to 1.26 liters per square meter per day.
Liters per square meter, that sounds quite good.
Yeah, they say it exceeds other state-of-the-art systems. So the key takeaway seems to be its versatility. It functions from really low humidity, 18%, up to over 90%.
That's incredible adaptability. What does that mean practically?
It means it could potentially be used year-round in lots of different climates. It could help in places with physical water scarcity, like North Africa, where there just isn't much water around.
Right.
And also places with economic water scarcity, like maybe parts of North India, where water might exist. But getting access is the challenge due to cost or infrastructure.
So it tackles different kinds of water problems, and this isn't just a tiny lab prototype anymore.
No, the device they tested was meter scale, about half a meter long, almost half a meter high.
Okay, so big enough to suggest it could be scaled up for real use.
That's the implication, yeah. It's the first time a hydrogel system of this size, working passively, has been successfully tested in these challenging real-world conditions.
That feels like a significant step towards practical deployment. What about cost? Is this going to be affordable? How does it compare to just buying bottled water?
That's a really important angle. They did a quick comparison. If you assume bottled water costs around, say, $2 a liter,
Okay, fairly standard in some places.
then using one of these AWHW devices could potentially pay for itself in about 9 days if you're in a high humidity area.
9 days, that's incredibly fast.
It is, even in low humidity conditions, like Death Valley, the payback period was estimated at around 25 days.
Still very quick. That makes it economically very attractive, especially for communities struggling with water costs.
Absolutely, it could make a real difference.
So how many would you actually need, let's say for one person's daily drinking water?
Well, the WHO suggests about 5.3 liters a day per adult for drinking. To get that amount in a really dry place, like 20% humidity, you'd need roughly 14.8 square meters of the hydrogel panels.
14.8 square meters. How many devices is that?
They estimate that's achievable with about 8 of the AWHW units, assuming each was maybe 1 meter high by 2 meters long.
8 units, taking up about 16 square meters of space, like a small parking spot.
Roughly, yeah. So a relatively modest footprint could potentially provide daily safe drinking water even in extremely arid environments.
That really paints a picture. Okay, so wrapping this up, this AWHW technology, it really does sound like a major leap. It's tackling safety, stability, efficiency.
Yeah, it seems to address those key historical problems directly while hitting impressive performance numbers across different climates. Safe, scalable, versatile. Those seem to be the headlines.
What really strikes me is that blend you mentioned, the advanced material science, with that clever origami structure and the smart passive systems like the cooling film.
It's a great example of integrated design, isn't it?
Yeah.
Not just one magic bullet, but getting multiple components to work together perfectly.
Makes you think, doesn't it? About what this kind of approach, combining deep science with smart, nature-inspired engineering, could mean for other resource challenges.
Sure.
You know, how technologies like this, leveraging basic principles in new ways, could genuinely empower communities, change the game for basic needs like water access, and maybe spark even more innovation down the line. It feels like we're just scratching the surface of what's possible.